So, let us look at this ring oscillator puff. Why this is important is because if you have an embedded system which has an FPGA, let us say, on board, and so it is reconfigurable hardware, right. So, you could essentially construct several digital circuits from them, is not it? You can easily construct them. So, ring oscillator is just an odd number of inverters which are cascaded with a feedback, right. So, if you, it is a very simple circuit. That simple circuit which has inverters which are cascaded, odd number of inverters which are cascaded with the output connected back to the input, creates a unique set of outputs, okay, for because of delay variation. This has been studied very well extensively over the last few years, and I will just recap everything into a big framework. So, here ring oscillator puff essentially captures the delay difference of a pair or group of ring oscillators introduced during fabrication process. Okay. When we talk about physically unclonable functions, we talk about so many of them: arbiter puff, ring oscillator puff, SRAM puff, butterfly puff, flip flop puff, buskeeper puff, bistable puff, and so on. So much rich amount of literature is available on device identity using physically unclonable functions. It is just that our imagination has to come, and perhaps we have to start using them. So, the issue really is, if you want to use them, you have to measure these variations, is not it. So, I think it is the best time now for IoT to succeed in making these measurements, because everything requires an apparatus. If you want to build an equipment or an apparatus on board, simple stuff, then that is an interesting area of system building itself, or electronic system building itself. So, if you just look at RO puff, it generates output bits based on delay difference between two identically designed ring oscillators. And why is it happening? It is because of manufacture variations. I said this already many times, but the trouble really is, alright, if you do manufacture variation, you are exploiting. What happens if these digital circuits, these electronic systems are applied different voltages? What happens if your rail voltages are different? Because most of the circuits today, or most of the electronic components today, work over a range of voltages. So, what happens if there is a voltage variation, and what happens if there is a temperature variation? This is also something that researchers have studied in the light of building very reliable ring oscillators. If there is a bit flip, okay, you can quantify this bit flip by applying some nice statistical methods, applying a little bit of probability study, and then you can essentially build an error correction system as well to introduce reliability in the measurement, right. So, just imagine that if you have an array of bits, and you know that consistently this there is one particular bit that flips, right, and the remaining are all okay, then how do you remove that? Either you should remove that, or bring in some amount of redundancy into the system, in some not redundancy, more in terms of correction of that bit, and to make it consistent, right. So, people have investigated error correction codes for building reliable PUFs as well. So, this is the area in which there has been a lot of research, plenty of research has gone in. It is good because it is something that has been there, and it is well known, by the way. Okay, so that is important. The next thing is, okay, you can do all these tricks in digital, but what about some tricks in analog? Can you do anything with ADCs? Can you do anything with DACs, and can you extract any signatures from them? The big answer is yes. Okay, there was a recent paper which I will point you to, which appeared in the year 2018, and this paper you can look up: repurposing SOC analog circuitry for additional COTS hardware security. So, this is something very interesting. Okay, so I can quickly tell you before we move on to some demo. I just want to tell you the following. Supposing you have an ADC, okay, ADC you feed in here. So, you have an analog, so this is an ADC, alright, you feed some analog voltage you feed. okay, you call this let us say V1, and I get a digital output. This digital output I will give it to a DAC, I will give it to a DAC. You must get back V1, but what you get will be V2. Now it is consistent that V1 is never equal to V2, not equal to V2, that is the real idea. So if you can have, and this V1 not equal to V2 is essentially across several chip. Chip 1 has some V1 not equal to V2, okay, some variation between V1 and V2, okay, and chip 2 same thing, V1 you read something, some other V2 you get. So you get V1 V2 here, and here you say V1 V2 prime, you get something else, you get here again chip 3 V1 you apply, you get something else. So you can see that as you keep changing the SOC, you start getting different variations in output voltages. This is something that one can exploit again and sort of uniquely identify a device. In essence, this is the idea of what this paper has been doing, and again it is trying to exploit the variations in silicon and so on. So let us quickly look up that paper and then move on to some simple experiment. Okay. Now the question really is, the authors have noticed that there is minimal research that has been performed with respect to commercially off the shelf available SOCs. Take the case of RO puff. The RO puff is nice, there is no problem at all, it is a nice way, people have beaten it quite well, have understood how to design reliable RO puffs, and you have seen the number variants and different types of puffs that in the digital world that you can build. The thing is, it is not that you have an embedded system with you and you can develop an RO puff around it, that is not going to work, because if you look at your own embedded system, you will have an SOC which perhaps has an ADC and has GPIO pins, has a radio perhaps inside, has a power supply component inside, has certain RAM inside, certain flash inside. So on top of that, if you have to build an RO oscillator, ring oscillator, that means you need additional configurable hardware which you have to put on board and then get that oscillator to be built. This is not going to be, you can't work backwards, or you can't do a retrofit of a RO of any of the digital puffs. Perhaps that is also the reason why the RO puff world has not really taken off after so much of good amount of research that has happened in that area. It is quite a mature area actually. So, here they have the authors have actually found that issue and said, look, if you take an SOC, you are bound to have an ADC, because sensors are going to be connected. In the IoT world you will have a lot of sensors. So an ADC will be there. So can I use an ADC? If I have a slightly sophisticated controller, I will also have a DAC inside. Okay. For example, there is one series of MSP 430 popular TI microcontroller which actually has a DAC inside it, and they use that feature in it, and then they show you that you can actually construct unique signatures from the hardware using analog blocks of a controller. So this is essentially what the paper is saying. Here is a very important point that you should note, that it is not that governments all over the world are not looking at it. The Defense Advanced Research Project DARPA agency DARPA is actually addressing hardware security within the packaging phase in the supply chain hardware integrity for electronics defense. It is called SHIELD. Please look up SHIELD, it is an active area, and DARPA itself is trying to address these very serious issues on device identification and so on and so forth. So that is essentially what the paper is saying. So as I said, this is to utilize analog components present in an SOC. So utilizing on chip analog blocks, using commercially off the shelf components, and use a MSP 430 microcontroller and see how exactly this can be exploited. Again it is the same story, process variations as documented in analog circuit is what we are trying to exploit here. Mismatches between transistors, capacitors, resistors, and even interconnects during manufacturing is what can cause identical analog circuit schematics designs to have markedly different responses that can be used to form the basis of a physically unclonable function. So, it is quite in detail, it goes on to into that. Okay. So, I will not go into the detail of this because really you may have to spend time understanding several aspects of this yourself, but you can see that there is a combination of ADC and DAC which essentially will lead to this idea of measuring V1 and V2 and trying to see whether V1 is all the time equal to V2 across all chips from the same same manufacturer, or is it different. It turns out that they use this MSP 430F2619 microcontroller, and they go, actually this paper is good because it goes one step forward and even says what do you do if you generate a unique signature, can I do a key generation. Okay. So, key generation using SOC analog functional blocks is also discussed. So, in F2619 there is a DAC connected to this chip via an analog mux, and they try to use this in the process of generating a signature. So, let us look at figure 2. Figure 2, this is the DAC output. Okay, the x axis is DAC input code, the y axis is ADC output code minus DAC input code, just a nice way of representing to show I would say a hard way of representing to show that it is a very unique way of the components. Ideally, of all the chips that they have tested, ideally if they are all supposed to work exactly the way they are supposed to give you an output, you should get 0, right. If you do V1 minus V2, you should get 0, correct. V2 is the output, V1 is the input, you have connected it from V1, you have connected it to a ADC. So, you got digital output, the digital output is connected back to a DAC as input, and that is given back as an output as analog, you get back V2. V1 minus V2 should be 0, that 0 is shown here. So, ideally your 0 line should be here, but not really true. The tests have indicated A, B, C, D, E, that means there should be 5 lines. You can see that there are clearly 5 graphs or 5 plots which show that there is a distinct variation between each one of them. In essence, this on chip measurement data of deviations between reported ADC code and expected ADC code for 5 different chips illustrates the device to device variation. So, you can also do a DAC output DAC input code, you have the same DAC input code and ADC output code minus DAC input code. Okay, this is another way of representing it. So, I would urge you to read this paper, but to tell you that this on chip exploiting analog components is a very good possibility for creating unique signatures for devices. Now, the big question that remains is how do I use that unique signature? Do I use it for key generation, and therefore I can use it for authentication purposes, or essentially what is it that I can use it for? That is another part of the story, but the fact that you can derive unique signatures from the different analog and digital blocks itself is an exciting area for device identity for the IoT world. So, here the key construction, this paper is also talking about how to construct the key. It is nice to read this paragraph to understand a little more in detail. Key construction after obtaining the measurements is the extraction of a binary value from said measurements. You after all need a set of bits, right, which essentially is your key. For on chip key generation, a simple technique is chosen which applies a DAC input code and then performs an ADC measurement n times to generate a total cumulative ADC count for the specified DAC input code. So, this essentially is the this result, I suppose, is indeed the way you do the cumulative count. So, you do n times to generate a total cumulative ADC count for the specified DAC input code. Once n measurements are complete, an ADC offset code is computed which subtracts the DAC input code multiplied by n from the cumulative ADC measurement. This ADC offset distribution is then analyzed and discretized in order to provide a meaningful number of discrete steps between the ideal 0 value and the measured ADC offset value. So, this in essence is shown in figure 4 actually. I think this is what, yeah, this figure 4 is showing you visual representation of key generation for 2 unique chips, and B is standard deviations between different DAC codes. Okay, so this is X, the first one is DAC input code, and the y axis is sum of n ADC output code measurements minus DAC input code times n, yeah this one, and this is y x axis is DAC input code, and the y axis is sum of n ADC output code measurements minus DAC input code times n. Okay, so if you plot you will get this nice little results, and essentially they do an experimental value verification of the key properties and all that, and then they show that yeah look, you can exploit the analog blocks, and they also do repeatability of output codes from 50 chip measurements on a single chip, and they find that it is a pretty nice way to generate a signature from analog blocks. So, the summary is you can do a lot of nice things even with analog blocks. That essentially takes you to what I was trying to get at when I started this discussion here, where I was showing you that UART, flash, GPIO, microcontroller, RAM, ADC port, analog sensors, oscillators, so many things are all potential for signatures, and somehow you should get to device identity security, particularly identity. If you want to find device identity, then replacement, counterfeiting are something that you could perhaps easily catch, and tamper of course will have to be somehow handled separately. Alright, so let us now move on to a demo. Okay. In the demo part, this is work done by primarily 3 people. One is a PhD student working here by name Girish Vaidya. He was assisted by one Suhas Sudhakara, who is a project associate, and then another person by name Vasant, who is a project assistant involved in this. So, they are a team of 3 people who were trying to understand, can we do something with respect to SRAM. Okay. They took a standard microcontroller like Nordic NRF 52832, which is a very popular microcontroller SoC, has a Bluetooth low energy technology built into the system. It has a RAM of about 512 kilobytes, and they said okay, let us see what we can do with this chip. So, before we go into seeing the demo, let us look at this SRAM itself, okay, little bit of detail into the SRAM, and then we will move on. See the SRAM, why the variations actually come, random variations in SRAM. It is very interesting for you to look at SRAM and design a puff around SRAM, because if you take the smallest possible IoT device which has an 8-bit microcontroller, has a sensor which is just giving you some binary output, like let us say you have a sensor which says presence or absence of humans. Okay. So, typically you would use a let us say a comparator based PIR sensor, okay, pyroelectric infrared sensor, which actually gives you an analog output, but you can put a comparator and say presence of human or absence of human, and just give you 2 levels. Okay, 0 means no human, 1 means human is present. You could just simplify the whole circuit, and most often that is how that is how it is used. So, if you take a very simple system like that, which is you do not need any sophistication there, then there also you will have some RAM, isn't it. So, that RAM can be exploited. So, you could perhaps seriously consider using SRAM as a possible hardware part for creating your unclonable function. So, let us see what you can do. Okay. So, the reason why random variations happen in SRAMs is because of doping concentration. I am just getting a little more detail so that you understand what do you mean by variations. It is basically because of doping concentration and channel length. Okay. You have these two issues and therefore, because of essentially when you talk about RAM, you are talking about inverters and pass transistors, right. So, a RAM comprises of inverters, digital I mean inverters and transistors. I will not go into the detail of construction of a SRAM cell, but essentially this is what it will have. So, all this doping concentration and channel length random variations is because of these two reasons. So, it is hard to reproduce, okay. Hence you have a nice probability of duplicating the hardware feature is close to 0, okay. Probability of duplicating the hardware, is I can't say 0, is low, I would say duplicating the hardware probability is low, is extremely low for instance, cannot be 0. So, it has to be close to 0. So, that would be a very guarded way of saying this whole thing. So, essentially the semiconductor variation that we are talking about, what does it mean? It simply means that the voltage transfer characteristics or VTC is different from one SRAM cell, one SRAM cell to another. That is the reason, and therefore you can actually go ahead and calculate the noise margins per VTC and all that. You can calculate the voltage transfer characteristics, calculate the smallest noise margin, you can do that. You can calculate the static noise margin ratio, you can calculate the you can do several things. Ultimately you are looking for fully skewed cells. If you have unskewed cell, there is there is practically no mismatch between inverters, okay, no mismatch in inverters. The cell can settle either to 1 or 0 depending on the noise. So, we can put that down. Unskewed you can either settle down to 1 or 0 depending on noise, okay. Then you can have partially skewed. What do you mean partially skewed? Partially skewed cell. So, unskewed cell, partially skewed cell. Here there is again little match. So, here there is answer is no match at all, no mismatch at all. Here there is little The answer here is little, here is no. I will just put it no mismatch, no mismatch, little mismatch. Here okay, fully skewed. This is interesting. Here we have high mismatch, high mismatch, okay, high mismatch between what? Two inverters which make up the SRAM cell. Thus what will happen? These cells, so here is the key takeaway, these cells consistently take on preferred power up value on power up. Okay. So, essentially I would say the startup the static noise margin ratio static noise margin ratio is far away from 1. Okay. Here it is SNM. So, I will just put for completeness you should say something about this, right. This is close to so I will say SNM, static noise margin ratio is close to 1, is close to 1. This is SNM ratio is equal to 1, okay, and this is away from 1. Here is the away from 1. Therefore, these cells consistently take on preferred power up values, that is PUV as they call the power up value, which is on power up they take a value, they take a preferred power up value because the static noise margin ratio is far away from 1. Okay. That I think answers the reason why the SRAMs essentially have the same startup values repeatedly when you reboot the system or when you power up the system. So, now what should the demo have? In the demo you want to essentially see whether whatever we have discussed, whether there is this kind of a phenomena actually occurring. So, let us start like this. I have Vasant here with me. We will set up this demo and I will start showing you some hardware and then we will move on to the physical demonstration. Alright, okay. So, this is the board of interest. What is this board? This is a commercially available board, you can buy it in any market. This is essentially the Nordic 52832 board. It has, as I told you, it has 512 kilobytes of RAM. It is a ARM Cortex M4 based system and we are trying to see whether we can replicate this SRAM puff in this demonstration. Okay. So, Vasant is here and he will operate the screen from the beginning. So, I would like you to look at the screen now. Yes, here in the screen we will first initially do a reset and the screen will show up. Alright, so here is a connection. Now look at what is happening. If you look carefully, he has selected 1 kilobyte of RAM out of the 512 kilobytes of RAM, and he is writing all FF into these locations. Okay. You can see all are FF, that means he is writing all ones into the location demo, all ones in 1 kilobyte location. Okay. Now let us see, after this what will happen, he will shut down the RAM, RAM is powered down, you power down the RAM and then check the power up value PUV. Okay. Alright, so it is still writing, maybe let us see what happens here. It is good to examine the screen here. So here is a small application program written by in embedded code which will allow you to do this experiment. Right, turning off RAM for 3 seconds and then it starts again and then he starts reading byte by byte, okay, just to see whether the values are actually matching. So you can see it says at RAM location, some RAM location you can see there is a pause here, RAM location is so and so, value at RAM location is this value, right. So he has been reading that he has been reading them. Now any number of times you do, it should read back the same values because the power up value should be the same, and let us see what he actually does. He has tabulated this result in a user friendly manner which will allow you to understand what is actually happening. If the startup values come back, he calls it that location as true, okay. True if the PUVs come back, PUVs come back. In other words, if it is fully, he will only identify those which are fully skewed cells, and then if they are fully skewed you will get back the same and then he will put a true there, otherwise he will say it is false. So let us say if you have 1024 locations, okay, how many of them come back with a true and how many of them come back with a false will be the final result that you want to see, correct. So let us do that and let us shift to the Excel sheet. So let us finish this, okay, let us finish this, yeah, it is done now. So let us move on to the Excel sheet, right. So you can see the left side is essentially the number of cycles he has done this experiment, and he takes byte by byte, he does a comparison. There is cycle 1 byte by byte, cycle 2, cycle 3, cycle 4, something like, I think he goes some 10 cycles before he does a comparison and shows you this beautiful table, false, 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 true, and so on. So you can see that you have to count every time it is true, only then it will actually relate to a count, right. So this perhaps cannot be used for or for total count because this is saying false. So first one, false, false, true, true does not make any sense. So you should see true, 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 only then you make it as a count. So let us see how many of them ultimately are in all the rounds, in all the comparisons that he does, how many of them actually indicate all true. So come down. So now let us see, yeah, so let us see that, okay. So here you go, you see a number here which says 300, and you can read it down below there, 326, just can you move the mouse there, yes, yes, little bit. So you essentially have 326 locations out of 1024 locations come back with the same PUVs. Roughly I would say a little of about 30% of the RAM locations can a little over 30% can give you consistent set of PUV values. But the task is not over here. What does it mean if the voltage rail voltage is the applied voltage is different? How will that change the game? Will this 30% become 20%? I would say a little greater than, a little greater, it should not be just 30, it is a little over 30, I would say, just write it as over 30. Over 30%, will it become less than 30%, will it be 15%? These are tests and investigations that one have to complete before one can use them in any useful, in any particular manner to generate a nice signature. So, in other words, this area of device identity using unclonable functions, signatures that are extracted from analog blocks and from digital blocks and perhaps all other blocks is a useful area one may want to pursue by reading up sufficient amount of literature in this area. You can come out with some nice algorithms and see how you can extract a signature first and then think about how can I use this signature. Can I use it for creation of a key, or can I use it for some other purpose of uniquely identifying? It is one's own imagination of how this data can be used. People even talk about creating sort of hash functions and so on and so forth, but that is all open how to use it. So, at this juncture I wanted to introduce you to this exciting area of physically unclonable functions as a security module as part of this course. Thank you very much.